Okay, welcome to Chemical Reactions, Chapter 11. Folks, this is where we get into some of the meat of real chemistry. In fact, the part of the definition of chemistry is how different atoms or substances combine and what do they produce. And basically that's what this chapter is all about. So, let's describe a chemical reaction. Now, if you look at this young lady here who's making bread, it looks like, she has flour and salt and yeast and water. This is what we call reactants. This is what goes into the reaction. This is before it happens. And then she puts it in the oven and she bakes it and bread comes out. This is called a product. She produced bread. This is what happens after a chemical reaction. Now notice that the materials going into it looks different than what came out because you've changed it chemically. The salt is still there, the flour is still there, the yeast is still, everything's still there. It's just in a different form. Okay? So you have things going in, but when they come out they look a little bit different. Now, parts of a chemical reaction. Some terms you're going to have to know. You're going to need to know the term reactant. I just used it a few seconds ago with the other slide. A reactant is the materials going into a chemical reaction. These things are what are going to react, which makes sense. The reactants react. The products come out of the chemical reaction. They are what are formed. They are produced in this reaction. So products are produced. Reactants yield products. Okay, reactants go into the reaction, products come out. One thing is, this arrow, guys, always, always, always points to the products. PP, it points to the products. This arrow has a term, we say it's a yield arrow. Reactants will yield products. Here's an example of a reaction. Iron plus oxygen will yield iron 3 oxide. This is what we call a word equation. We could write it in formulas. Iron, Fe, plus oxygen, O2. But you're wondering, why am I using O2? Why not just O? Oxygen's O. Remember, oxygen, guys, is one of those 7 diatomic molecules. It must have this 2 here. You cannot just put the O. It has to have the 2. So iron plus oxygen yields iron 3 oxide. Okay? And notice over here, iron does not have a 2 because it's not one of the 7. Remember, hydrogen, nitrogen, oxygen, fluorine, bromine, chlorine, and iodine. These are your 7 diatomics. They have the green dots on them on the periodic table. They're the ones that have to be H2, Br2. They have to be diatomic. Okay. Now here's another example of a word equation and the formula equation. Word equation is hydrogen peroxide yields hydrogen and oxygen. The formula equation would be H2O2, which is my hydrogen peroxide. Now this symbol right here, folks, is called a state symbol. It tells us that hydrogen peroxide is in a liquid state. Okay? Hydrogen peroxide decomposes into hydrogen gas. That G stands for gas. Notice it's diatomic. It's one of the 7 diatomic molecules. And oxygen gas. This is my formula equation. Here are some symbols you'll be expected to know and use in your reactions. The plus sign basically separates your different substances. Basically, when you look at it, if you have like hydrogen and oxygen, H2 plus O2, it just separates your 2 substances. This arrow means to yield or produce. It separates your reactants from your products. This double arrow here is an arrow that shows a reversible reaction or something that's in equilibrium. It goes back and forth, so it's a double arrow. The S designates you're in a solid state. These are my state arrows, your state of matter, or state symbols. S is for solid, L is for liquid, G is for gas, and A is aqueous. It means the substance is dissolved in water. It's not just liquid, it's actually dissolved in water. The crystalline substance, which is probably a solid at one time, is now dissolved in water. You'll have an arrow sometimes with a little triangle over it. That little triangle has got a name. It's called a delta. This delta means you've heated it. You could write heat over if you want, but I kind of like drawing the arrow. And sometimes you have a symbol, a chemical symbol over top of the arrow. This indicates that a catalyst was used in the reaction. Now, a catalyst will speed up a reaction without becoming involved in the reaction. And we'll look at some of those as we start doing these reactions. Okay, now let's look at balancing chemical equations. If you look at this reaction here, hydrogen plus oxygen yields dihydrogen monoxide. Well, let's look at what's going into and out of it. I've got hydrogen. I've got 2 atoms of hydrogen here, and oxygen, 2 atoms of oxygen. But on this side, for my hydrogen, I have 2 atoms, but for oxygen, I only have 1. I mean, there's 1 down there. This is not balanced. This cannot happen, folks, because of something called the law of conservation of matter. Remember that? The law of conservation of matter, or mass. That matter can neither be created nor destroyed. It's just changed from one form to another. Mass can neither be created nor destroyed. It's just transferred from one thing to another. Okay? This cannot work. You must balance your equations. Always, always, always balance them before you do anything else. So if you look at this one, I have H's. Now look what happened. A number was put in front of here. And I multiply that number in front by the subscript, and I get 4 hydrogens. There's a 1 in front of this oxygen. The 2 does not go into the oxygen. This plus stops it. So there's 2 oxygens. My hydrogens, 2 times 2 is 4. 2 times 1 is 2. Now it's balanced. Now it's okay. We can move on. Let's look at that a little bit more. And let's look more at what's going on with this reaction, some names and stuff. Okay, first, have you ever made cookies? Okay, let's kind of look at this. Making cookies is like a chemical reaction. If I have 1 cup of sugar plus 2 eggs plus 2 cups of flour plus a half a cup of oil will give me 24 cookies, let's say. Okay? This 1 cup, this 2 eggs, 2 cups, half a cup of oil, 24 cookies. That tells me how much of something I'm going to be using. That's what this number here tells us, guys. This is called a coefficient. A coefficient. This coefficient tells us how much of something. It can either be a mole, it can mean molecules, okay? So when we look at the coefficient, this is how much we're using it. Coefficients can be changed, okay? I can actually change this number. Just like if I was working with cookies. What if I didn't want to make 24 cookies? What if I wanted to only make 12 cookies? Well, would I still use this big recipe? No. I would use a half a cup of sugar. I would use 1 egg. I would use 1 cup of flour. And I would use 1/4 of a cup of oil. I just divide everything by 2, right? So if I didn't want to make 2 moles of water, I could use 1 mole of hydrogen and a half a mole of oxygen and make 1 mole of water. It's the same thing. A recipe is just like a balanced equation. What goes in is going to come out. And if you don't use the right proportions, it's not going to be very good cookies. Okay? So when I look back at this, then this is my subscript. My subscript can never be changed. Cannot change. No change. Okay? This tells me how many atoms of that element I have. So I have 2 oxygen atoms here. 1 molecule of oxygen with 2 atoms. Okay? So here's my coefficient, and this is my subscript. You can never ever change the subscript. You can change the coefficients if you want, but you may not change the subscripts down here, okay? So, let's look at something else here. This shows you the makings of carbon dioxide. MCO2, I'll make it a little bit bigger here, which is a gas. You have one molecule, one atom, one mole, whatever you want to call it, of carbon, which is solid. You're going to add to it one molecule, one mole of oxygen. And this makes one mole, one molecule of carbon dioxide. This is a gas too. Okay? And this is a balanced equation. Sometimes they just balance themselves. You don't have to worry about it. But this can be changed. What if I wanted to make 5 moles of carbon dioxide? Well, I would have to use 5 moles of oxygen, and I'd have to use 5 moles of carbon. I can change my coefficients, but notice I've never changed that 2 down there or this 2 down here. I cannot change this. Let's look at balancing. Okay, now we balance by something called inspection. When I inspect it, I say, okay, how many nitrogens on one side, how many nitrogens are on the other. So I draw a line down the center like this. I put my elements on this side, nitrogen and hydrogen, and my elements on this side. I have 2 nitrogens over here and 2 hydrogens on the reactant side. 1 nitrogen and 3 hydrogens on the product side. Now, I need to balance this equation. If I've got 2 hydrogens here and 3 on this side, I look for my least common multiple, which is 6. So I'm going to put a 2 here. 2 times 2 nitrogens is 2 nitrogens, and 2 times 3 hydrogens is 6 hydrogens. If I have like 2 NH3, guys, that 2 multiplies throughout, just like in math. Distributive properties there, okay? So now I have 6 hydrogens and 2 nitrogens. Well, my nitrogens are balanced, aren't they? So if I put a 3 here, I've got 6 hydrogens. 1, 3 to 2. That's my ratio in this recipe. Okay? Let's look at the next one. Draw my line down. K, Cl, and O. K, Cl, and O. I have 1 K, 1 Cl, and 3 O's. 1 K, 1 Cl, and 2 O's. Once again, least common multiple. I'm going to put a 3 there. Gives me 6 oxygens. 3 times 2 is 6. And over here, if I put a 2, well, now I've got 2 potassiums, 2 chlorines, and 6 oxygens. Okay, my oxygens are balanced. If I put a 2 here, I get 2 chlorines and 2 potassiums. It's all balanced. You really don't have to do this area down here, guys, if you don't want to. This is just a tally area. It just helps me keep track of it. If you don't want to do it, you don't have to. It's just called by doing it by inspection. Let's try it without it once. 1 sodium, 1 sodium. 1 chlorine, 2 chlorines. Uh-oh. Let's put a 2 there. Now I have 2 chlorines, 2 chlorines, but unfortunately I have 2 sodiums and only 1 over here. So if I put a 2 here, 2 sodiums, 2 sodiums, 2 fluorines, 2 fluorines. So I am now balanced. It's a 2 to 1, 2 to 1. I write it like this, 2.1.2, like that. It shows me my ratio. Now when you come to something like this with parentheses, you do it the exact same way. I have PB, O, H, and Cl, PB, O, H, and Cl. The reason I do it like this is to keep them in the same order so I can see what's going on. Okay, so I have 1 PB, I have 2 oxygens, because 2 times that 1 is 2 oxygens. Now my hydrogens I have to add together. I have 2 here and 1 there, so I have 3 hydrogens and 1 chlorine. 1 lead here, 1 oxygen here, 2 hydrogens, and 2 chlorines. Let's look for the easiest fix first. Well, let's get my least common multiple for these hydrogens. So I'm going to put, ooh, that's not going to be good because I've got 2 different hydrogens here. Let's try to do something else. Let's put my oxygen. Let's put a 2 here. That way I'll have 2 oxygens. 2 oxygens. So I have 4 hydrogens now, don't I? Okay? So my oxygens are balanced, but my hydrogens and chlorines are not. So what if I put a 2 here? I get 2 hydrogens on this side, 2 hydrogens on that side, and I get 4 hydrogens on the reactant